welcome. In this lecture, I want to go through, I'm going to go through pieces of the fact that M2Z is actually a ring. And one of the pieces that I want to go through is to show that it's additively closed, right? Because in order to show it's a ring, you need to show it's both additively and multiplicatively closed. But I think that if you see me go through it being additively closed, that this will help in seeing how you would prove in general that something is additively closed. And what does that really mean? That means that anytime I have two elements of the ring and I add them together, so in this case, anytime I have two elements of M2Z, or 2 by 2 integer matrices, and add them together, I get an element of the ring, so an element of M2Z. That is a 2 by 2 integer matrix. So this is a for all statement, right? So kind of breaking it down, this tells me here, so looking at this is a for all statement. So we'll need that A, A, B in M2Z are arbitrary. Right? And then this is kind of like, or like an if then, and so then we're going to need to show this part is true, right? So we'll need to show. Okay, so let's just kind of get started with kind of the first part. So I know that I'm going to need to set those to be arbitrary. Okay, so this is the proof. Okay, so we want to, oops, I want that the same color as over there. So let A and B be arbitrary elements of M2Z, okay? And now, so you can guess, so what are we going to need to do next, right? And I can kind of annotate some more over here, is that this gives me a way to write A and B. So me kind of by the definition of M2Z, a way to write A and B. Okay, let A, B, B. So by the definition of M2Z, I know that there's going to exist, so there exists, right? And then I'm going to have, so I'm going to have A, B, C, D, E, F, G, H in the integers. So that, right, A equals A, B, C, D, and B is going to equal E, F, G, H. Okay? Because the definition is an existence definition, we've talked about this a number of times, that when you have an existence definition, it gives you a way to write elements. You need to make sure that you're only saying there exists. It's not a for all statement, it's a there exists statement, but it gives you a way to write elements, which will then give you something to work with, because now I can just add them together and see what I get. Okay? So now, in the next step, I'm going to have that, so A plus B, so now I can write the sum of these is going to equal, well, it's going to equal, we're just going to do this kind of coordinate-wise, so it's going to equal A plus E, B plus F, C plus G, no, D plus H. Okay, now, since A, okay, so since Z is additively closed, right, we know that A plus E, B plus F, C plus G and D plus H are all elements of Z. Okay. Now this is actually very common in these types of settings, that you're going to use that the property holds in this example for the integers, right? So we're actually using that the integers are a ring, and then so we manage to take our elements, write them in terms of integers, right? So that the sum is in terms of integers. We can use the properties of integers, namely this. So since Z is additively closed, we know that these are in Z, and thus, by the definition of M2Z, right, we have A plus B has to be in M2Z. Okay, all of its entries are integer. Okay, since we have shown A plus B is contained in M2Z for all arbitrary AB in M2Z, we have that M2Z is additively closed. As desired. Okay, so what have we done here? So we're taking what we knew what we needed to do was to take, right, because this is a for all statement here, we're going to need to take an arbitrary A and B and show that their sum is actually in M2Z. So we start out with that. We just let these be arbitrary. And then, now this is one of these circumstances where we can use the definition to translate them into some generic form that we can work with. So we do that. This is our generic form because we're in M2Z. And now we have, when we add them, we have something that's in a nice form that we can work with. And we can use actually the fact that the integers are a ring and additively closed, so that each of these has to be in the integers, which tells us that A plus B is actually in M2Z. And then really after that, we're just kind of wrapping it all up together. But it is one of these circumstances where write something in a generic form, you know, use the properties that you already know about something else, and then bring it back to show that what you have is indeed satisfies the properties that you want. Okay, so I hope that was, made a little sense and was helpful and useful, and I will see you in the next lecture.